Still got 4, so.
Can you, yep, it's working. So check the input volume on here, like go into sounds.
Okay.
So we can see while I'm talking if it's registering it. So go to input, yeah. Okay, so it's registering it.
Oh, nice. Okay, so that
Yeah, I mean, you could actually turn the output sound on, and then we could actually hear if it, like, this live streaming is hearing it too, instead of checking the other room, but.
I can check it.
Oh, there you go. That would also work. I mean, at some point, definitely should probably check the other room, but.
So hard.
The 2-minute delay really throws you off, though, so.
Also work. I mean, at some point. Testing one.
Testing. Testing. No. What? Should? Okay.
She's checking the other rooms. She's talking.
Okay.
We just go keep going testing 1, 2, 3. I can do it if you don't want to.
Thank you.
Testing 1, 2, 3. 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 Okay. Testing 1, 2, 3. 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 Testing 1, 2, 3.
Hello? Great. All right, good morning, everyone. So this morning, we are going to be starting the Chemistry Ecosystems Climate Session, and it is my pleasure to introduce our keynote speaker for this morning, Jean-François Lamarck. Jean-François is a senior scientist at NCAR in Boulder. He got his PhD from the Université de Louvain in Belgium, and then he did a postdoc in the Advanced Studies program at NCAR, and he has been at NCAR since then with a brief foray out of down the street to Boulder, in Boulder to NOAA. He was the head of the radiative forcing chapter in the last IPCC in AR5. He is really a well-known figure in the chemistry climate community and has really worked with a lot of initiatives, CCMI, CCNIP, being really heavily involved in all of that work. And he is currently the chief model scientist for CESM. So it's a real pleasure to have Jean-François with us today. Jean-François?
Should I use this thing?
Oh, I don't know. Use this or the mic?
Oh, the hand mic? Okay. Feel like a rock star. Good morning, everyone, and thanks for being here. So, Danielle contacted me a few months ago, and to see if I could talk about CESM. So CESM is the Community Earth System Model, and so what I will go through in this brief presentation is kind of an overview of CESM, and just because I'm not sure how many people here are familiar with CESM. So please feel free after my presentation to ask any questions, and I'll be here all day, so please feel free to ask me any questions. So this is what CESM consists of. So this is another system model. So we started about 20 years ago putting an atmosphere, and then we decided we need to put land, and then an ocean, and sea ice, and then this has been growing into bringing now more and more of the Earth system characteristics of it. And so there is a full representation of biogeochemistry in both the ocean, the land, and atmospheric chemistry in the atmosphere. We've also now are considering an explicit representation of land ice, glaciers, and also a new introduction very recently was surface waves, trying to represent mixing in the ocean. So one of the topics that's been discussed is there a way we could bring geochem into CESM? And so there will be a discussion between some of you today on what that would look like, but my talk will be about why would you even want to do that. So it's going to be kind of a discussion of what is in CESM that might be of interest to geochem. So CESM, as I said, is something that has expanded over the years, and for better or for worse, it's a model that constantly evolves. And this is over, say, the last cycle of major releases. We're about to release next month, hopefully, in about 6 weeks, the new version, CESM2. And CESM1 is about a 2010-2011 model, and there's been continuous evolution. And this is just one example. Is changes to the representation of atmospheric physics, and they're always, I mean, we don't do it just to change, and there's actually good reasons to go with better representation of clouds in this case. And this is what we call the club parametrization, which gives us the ability of having a representation of the aerosol indirect effect by having a much better representation of cloud microphysics. And so this is kind of where we stand. We haven't really changed the atmosphere too much over the last 2 years, and so we're finishing this. And I will spend just a couple of minutes on trying to show some of the improvements that we're seeing. And so this is going to be very climate-centric. But this is where we started. And there is this large ensemble that was performed which was a set of simulation with an extremely long pre-industrial control, the way models are initialized in general. And the advantage of that, it gives you a really good sense for internal variability, so which is a huge element in climate modeling. And so this is one stretch of 100 years of the pre-industrial control. And the expectation for precip is that it hasn't changed significantly between pre-industrial and present day. So between, in the mean. And so these are the OBS. And this is CESM1. And we're on the same planet, it's not that bad. But there are some features that have been kind of long-standing in the climate community, which is called the IGC8, where we tend to have very parallel bands in the tropics, especially in northern wintertime. And so for the first time, we've actually been able to really reduce the size of this IGC to have a representation of the South Pacific convergence zone. And this is kind of an amazing achievement, which is a representation of what it means to change all the parts of the model. And this is not something that we were particularly targeting, but this was a result. And this is another one, which, again, going back to the climate model by itself should be able to generate the modes of variability that nature is seeing. And that's one of the advantage of a full representation of the climate system, is that it looks, hopefully, like the real world. And so this is, again, where we started. This is the MJO, modes of precipitation, going across the Pacific, one of the main modes of variability of the tropical regions. So it's pretty important to get that. CESM1 did not get any of that. It doesn't really matter how you look at it, it never propagates compared to the observations. This is what CESM2 gives right now. And these are just examples we have, and so that looks really good. So we seem to have a really good representation of the way nature changes. The way we've building this is through a collection of working groups. And we have, similar to this meeting, we have an annual meeting that's going to be in June, where we have 350, 400 people, depending on the year. And this is the interaction of all those groups that makes CESM. So CESM is not driven by the atmosphere or by the ocean. It's trying to get all those people to work together to build the best Earth system model. So it might not be the best atmosphere model. We might be able to do a better atmosphere model, but there might be at the risk of really screwing up the land biogeochemistry, for example. So I'm there in the center getting all the criticisms. So what we try to do is to have a single system, and so with the ability of, so if you go back to this original figure, what we have is a way, we try to build a system where with the same level of scripts and knowledge, you will be able to run a model either with just the atmosphere and the land, or the whole thing, or just the ocean. So we try to have a way of cutting the pie, because it's really key to the understanding of how the system works. So we try to have everything in a single framework, and then we have what we call concepts. So it can be pretty daunting at first, because there are so many different possibilities you can cut this problem, right? In terms of the atmosphere, we have three standard configuration. And I believe this would be probably the most of most interest to this group. It's what we call the low-top model, which goes up to 40 kilometer. We have also a high-top version, which really gives us a good representation of the stratosphere, mesosphere, which is called WACM. And now we're going into space weather, where we go up to 500 kilometers, and it's WACM-X. We're going to be running out of WACM versions here pretty soon. But WACM-X is really looking at ionosphere interaction with with the sun, and so this is very, very, very different chemistry and physics up there. So as I said, we can usually use the model, the atmosphere model, fully coupled with all the components, or with specified SSTs and CIs, so that you let the model do its own thing. So it's fully consistent, but you specify the observed sea surface temperature, or you just specify them, and CIs, or you can also run it in more as a CTM by using specified dynamics. Usually we use Mira, but it can be anything. And it's almost always coupled to the land model. And then we'll go with why we want to do that. Different dynamical cores. So our chemistry, although this is not really the topic of discussion, is for people who are interested, is based on Mozart, and we have a flexible chemistry approach. We can go from the troposphere to the ionosphere. The chemistry is always coupled to the modal aerosol scheme, which is the scheme that we have in the atmosphere. MEM4 is the standard one. We also have MEM7. So the advantage or disadvantage is that you have the aerosol indirect effect. The clouds are always responding to the aerosols. And then one thing that's actually been really fun is we're now doing volcanic emissions volcanic aerosols directly from SO2 emissions. So we put SO2 emissions like Pinatubo, put SO2 10 kilometers, 10 teragrams, and boom, and then you let her rip, and it gives you an amazingly good representation of volcanoes. But so we put SO2, but it could be anything else, right? It could start putting halogens and other really cool things. We specify emissions, and the wet removal, although this might, if we start bringing geochem in here, this might not be relevant to what you do, depending on how we're going to couple geochem to CESM. So some of the really important things to me on using CESM is not so much the atmosphere, but much more the coupling to the land model. And so all the dry deposition is done in the land model. The reason to do that is that you have access to all the information at the plant functional type level instead of having an aggregate. And also it means that you will have information about land use change. So if you're going to do long transient simulations, you will want to look at the importance, or you might want to be able to tinker and identify that. Nitrogen deposition, both for MNOI and NHX, will impact the carbon cycle. So we have a full biogeochemistry of the carbon and nitrogen cycle. So nitrogen deposition impacts the carbon cycle deposition. And then the biogenic emissions, we have currently Megan. We have dust emissions and fire emissions. So this is not specified fire emissions, but it's the land model has triggers, because this model is used not just to represent the recent past for which we have observation, but we will use it for pre-industrial control, present, historical, future, paleo. So we have to have, and this is a key part of the carbon cycle, and the internal representation of fire. It's a big disturbance, so you have to make sure you have that. And one thing that is present in the model, although we haven't really explored it because our current OH in the atmosphere is not really good, and so we can't really do interactive methane with any credibility that I would see. But we have wetland methane emissions. Then the counterpart is then the ocean. What are the ocean? What are you getting from the ocean? Why would you want an ocean? As I said, the ocean doesn't always have to be turned on. You might want to turn it on, but it becomes more expensive and become an even more variable system. So climate system is very variable, and it's going to be a major drain on resources to use a climate model. It's much more difficult to isolate signals from simulations than when you use specified dynamics. So the same thing, we have the dry deposition is being handled by the ocean, whether it's specified or interactive. And then in the interactive model, we have nitrogen deposition that impacts the nitrogen and the carbon cycle in the ocean. Same thing, we have black carbon deposition on sea ice, sea salt emissions, halogen emissions, although those tend to be mostly in the specified only version. And then a few years ago, people might be aware there was a representation using the biogeochemistry in the ocean, which has all phytoplanktons and representation of different critters in there. We had DMS fluxes, but that's kind of been lost right now because we're doing revamp to the BGC. So what are typical applications of CESM? And CESM tends to be built mostly, but not solely, for long-term simulations. So that's our bread and butter. There's like CMIP6 type simulations. And so that in and of itself requires having change in emissions, land use, long-lived greenhouse gases, ozone-depleting substances. And so there is all that machinery that's already built in CESM. You can look at land use and how it's going to affect BVOCs and how that's going to affect SOA formation because it's built in over long time scales, even paleoclimate. As I mentioned, internal variability is a key element here. You have to understand what is driving the changes that you're seeing in a simulation. Doing simulations with a climate model, by the nature of having different weathers all the time, means that just doing a one-to-one comparison is really dangerous. You have to be very careful that you know what is the internal variability in your unforced system, what is the changes that you're expecting, so that any difference that you see in your analysis study has to be beyond the noise that's just being generated by the internal variability. So that's a key element that has developed over I'd say the last 5 to 10 years, is really the importance of this. And I have a few slides, but I don't know if I have time to discuss that. And then the counterpart is something much more maybe similar to what is done here, looking at short-term campaign type simulations using specified dynamics. We also have data simulation through the ensemble Kalman filter DART, mostly on CO and aerosols. So just as an example of this is where we are getting ready for CMIP6, and running CMIP6 will require running about 5,000 years of the Wacom version. So that's 150 kilometer, 1 degree in the atmosphere, 1 degree in the ocean, about 200 some species, 70 levels. It's huge, huge thing. But we have made the model fast enough that we can run those things within approximately 6 months or something like that, because we get about 6 years per day. And then the low-top model with much simpler representation of chemistry, basically fixed oxidants, gets about 20 years per day. And so this is the type of process, how long it takes to really build a model that you can use for CMIP6. The good thing is that once you have built this model, then you can use it for a lot of studies because you have built the pre-industrial control that's really long. One thing that's going on right now that might be of interest to this group is the regional refinement. And so we don't go with an embedded high resolution regional model, but we go with variable resolution. And in this case, from about 100 kilometers in here to about 14 kilometers in here. So these are 3 levels of grid, and you'd be hard pressed to see any problems of transition among the resolution here. The advantage is that you have a full feedback. So whatever system goes out can come back in. And so we're exploring this. This is very, very recent, like a couple of weeks ago. And we're going to be looking at putting chemistry in that. And so this is all I have. I know it's just an overview. There's nothing really substantial. This is another example from the ORCAS field campaign. Those were forecasts of CO2 and oxygen anomalies that were used for flight planning. And the way we got that was to have Matt Long, not your Mike Long, and to drive the ocean model with the biogeochemistry with the observed winds. And so it was a specified dynamics forcing the ocean and the biogeochemistry leading to a measure of the fluxes in oxygen and CO2. This is just the zonal mean cross-section across the atmosphere. This is the surface values. And so this is the kind of things that might be of interest to these groups once we couple it to geochem. And that's all I have.
Questions for Jean-François?
Does CSM have different options for the different representations of processes? You give us kind of a streamlined view of CSM.
So, yes. So, for example, there's those previous physics are still available, right? See, so there is a variety of things you can do. At the same time, to get to this point, you have to focus on one set, one configuration, resolution, choice of physics, choice of parameters, I mean not emissions or something like that, but you have to choose the parameters in the physics that you need because it has taken about 2 years to put the model together so we started with the physics for the atmosphere about 2 years ago, and we are now finishing putting everything together. I mean, there was evolution since then, but it takes, I'd say, at least a year to put the model together, such that in a fully coupled fashion, it works as well as we want it to work. So, yes, you have choices, but those are not what we call validated. We've done probably about 5,000 years of simulations to get to this point. And so we can't do it for too many configurations. We'll have another one, there will be a high resolution quarter degree atmosphere. But those are going to be the two main ones. The other ones, some of them will be slightly studied, and then there will be that documentation. And then there's everything else, which is use at your own risk. It should work, but scientifically we have no idea because we cannot go through this process for all of those.
I have a couple of questions about the last one. First question is, how do you do fire emissions with the land? Is it somehow coupled with what's going on in the land model?
Yeah, so Feng Li, I believe, is the person, that's right, is the person who has been developing the parameterization. He has dependencies on load, temperature, humidity, triggers. I think they built in some dependencies on GDP, and such that you do have actually a fairly reasonable representation of the evolution, well, over time, with what we know of biomass burning 100 years ago.
So just to follow, so I guess if we put geochem into CSM, given that coupling to land, we may not be able to do apples to apples comparisons between a standalone benchmark geochem one here versus how it's operating in CSM.
Right, so you can always overwrite whatever emissions you want. You can say, I want isoprene to come from files or Megan, right? So you don't always have to have Megan. You have Megan if you want to. If you want to have it specified from a file, you can do that. Same thing for the fires. You can say, no, I don't want that stuff. No, dry dip right now is really tied to the land model. If you want to get rid of that, and all the good work of Maria, then Right. No, I agree, and that will be something that you might want to do. There are ways around it. We can find ways to do that, probably by specifying negative fluxes at the surface.
Maybe we'll let Lee take the last question.
So, GSM, of course, has a long history of coverage with the GIS model. Aside from the obvious major benefit of the carbon cycle, do you see any other major possible benefits of carbon mechanics relative to GIS?
Yeah. And joke apart. I think there is probably more development in terms of the number of people who are involved in some of those aspects at the periphery, like the carbon cycle, the nitrogen cycle, all that, then there is, that's my understanding, then there is at GIS, and same thing on the ocean. And that's where I think that aspects of the Earth system model, which I think is really, what I sense would be the most useful for GeoSchem, might be more studied, because there's just more people looking at it, and I think there's just a lot of interest, and so you know that there is going to be a lot of development going that way. So, and there's my politically correct answer.
Okay, thanks, Jean-François.
Thank you.
Great. Okay, we're going to be continuing with the speakers. The next speaker is Amos Tai from the Chinese University of Hong Kong. I'm just going to say to all the speakers this morning, I'm going to show you the green 2-minute card at 7 minutes. So when you see that card, you should wrap up. And also, when people are taking questions, it would be great if they could repeat the questions so folks on the webcast and in the other room could hear them. Thanks.
All right, thank you very much for the introduction. And so today I'm going to talk about how the interactions between CO2, ozone, and vegetation would have implications and would influence atmospheric composition, air quality simulations. Especially, it may be relevant for people who will be looking out to run historical or future simulations where CO2 level and ozone level may be very different from present day. All right, so okay, so let me start with CO2, which would have different impacts on atmospheric composition through various pathways, including, as you can see here, it inhibits isoprene emission for reasons that plant biologists are still not very sure about. It would enhance LAI through CO2 fertilization just because plants love CO2. And at the same time, it reduces stomata conductance, which means it would increase stomata resistance. And of course, all of these things would ultimately affect biogenic emissions and dry deposition with implications for atmospheric chemistry. So we'd like to be able to represent these processes in GeoSchem, and thus we add a activity factor, activity scaling factor for CO2 as a function of basically to isoprene emission. For LAI effect, we have to run CLM 4.5 biogeochemical mode, which is the land model of CSM, and under transient CO2 concentration to get the relative changes in LAI. And for stomata resistance, or conductance, we parameterize the relative change in stomata conductance using this model equation. So these are what we put in GeoSchem, and these are the sort of experiments that we've done. And we start out basically wanting to examine the responses of ozone to land use change under different future scenarios. That's what actually the original purpose of the study. But then we're interested to see how additional or how elevated CO2 in the future may bring in additional effect on top of the effects of land use change. So this is what I'm going to focus on today. So as you'll see here, this is an example from RCP 8.5 CO2 level, which is about more than 500 ppm. Under that conditions, isoprene emission would be reduced by 30% because of inhibition, and that would then lead to a reduction in the ozone level by up to about 6 ppb. At the same time, stomata conductance is reduced by about 30%, leading to an overall increase in ozone because of reduced dry deposition. And the effect of LAI changes because due to CO2 fertilization is indeed much smaller. So the combined effect is really kind of like the compensation between the isoprene inhibition effect and stomata conductance effect, which by themselves are pretty large, but they can be quite large, but they kind of like offset each other, making relatively modest changes to ozone overall. All right? So that's about CO2. What about ozone? So ozone would also damage vegetation. It damages photosynthesis, and LAI, it also reduces stomata conductance sort of separately. In another study that we just published recently, we actually used CSM alone without geochem at all to look at the coupled effect of all of these things on and the effect on feedback effect on ozone. But here I'm going to focus on some newer work that we've done using geochem. So what we did is basically to implement, we used the Lombardozzi scheme, ozone damage scheme in CLM. We run CLM at different ozone levels, and basically we parameterize the simulated relationship between ozone and LAI, basically by fitting a function like this. So this is a function for the relative changes in LAI under different ozone level. So basically I fitted this function into the simulated result from CLM. So you can see that this function is more or less like an exponential decay function as a function of, like the relative changes as a function of ozone level. So this is this is a much simplified form than, having to run the whole CLM. And so this is what we put in GeoChem in order to see how ozone and LAI may be coupled in GeoChem. So this is how we did it. We first have to derive the potential LAI that is unaffected by ozone, because what you observe now is actually the outcome of ozone damage already. So we would want to know what would be the potential LAI if there's no ozone damage at all. So potential LAI is then the observed LAI for MODIS divided by the gamma factor that we parameterize. So this is how we sort of implement it in GeoChem. We run GeoChem for instance, for a month. We simulated ozone for a month. So basically, we ask GeoChem to read the mean ozone concentration of the previous month, calculate the gamma factor, and then apply this gamma factor to the potential LAI that we have derived. So we have the ozone affected LAI, which would then be used to drive the simulation of ozone in this month. So this would then just carry on and sort of until the system until the system goes to equilibrium. I mean, you're having a kind of semi-steady monthly mean ozone concentration and monthly mean LAI. So basically, this is kind of like an online ozone LAI coupling on a monthly time scale. So this is the result, and so as you can see, when we coupled ozone LAI on a monthly time scale in GeoChem and run for, actually this is the result from 3 years, we should run more, but this is the result that we have done after 3 years of simulation. Basically, summer LAI would be reduced by actually up to about more than 2. The LAI can be reduced by 2 because of the ozone damage, and simultaneously the changes in ozone is roughly about -1 to about +3 ppb. Okay, so we do quite a number of sensitivity studies and also look at different variables to really want to see what made these changes. So what created these changes? So basically, whenever you see increase in ozone, like here in this region, in Central America, Africa, in America, these positive changes, or so to speak, a positive feedback effect of on ozone. Positive ozone feedback is really reflecting how dry deposition, reduction in dry deposition, which in most places more than offset the effects of reduction and isoprene emission. Okay, because these two effects usually have opposite, sort of opposing effect, and dry deposition is kind of like play out and win the competition. But you can also see there is some reduction in in ozone in places where we actually don't see significant changes in LAI. So this is just, we believe it is actually due to the reduction in PAN, especially we observe great changes, reduction in PAN in the in Europe, and which is associated with a reduction in isoprene, and we thought this could be the effects of reduced transport. So to conclude, we found that elevated CO2 in the future can suppress isoprene emission, stimulate conductance, leading to basically compensating effects on surface ozone. Effect of CO2 polarization is relatively small. The combined effect is actually in the range of about -1 to 4. At the same time, ozone-induced damage on LAI can also lead to an ozone feedback of up to +3 ppb. But you can really see that these magnitudes are not like very large. It's not because like the impacts is small. It's really because, or it really reflects the compensating effect of different pathways, which often offset each other, and which by themselves can be important. So just to summarize, just to like mention some ongoing work and to see if like some people would be interested, sort of working together on this. We will definitely continue to parameterize ozone damage on stimulator conductance, either using CLM and also using another model that we recently developed, and we would want to look at how ozone and CO2 together can affect ozone in the future, basically affect atmospheric chemistry in the future. Well, we have started to put the Farquhar-Ball-Berry model in GeoChem to calculate stimulator conductance, and that is exactly how it is done in CSM right now. And as a pastime activity, to kill time, to relax myself, I actually wrote a terrestrial ecosystem in R because I just love R, and this is driven by Mera2 and just FP. So for anybody who would like to calculate photosynthesis and stimulator conductance and that sort of things, totally consistent with the input metrology for GeoChem, then, and if you want to run it in your own computer, or if you hate CLM, I'm more than happy to share with you. Okay? All right, so thank you again.
Unfortunately, we don't have time for questions, so if you have questions, maybe you can get Amos in the break. The next talk is going to be by Sam Silva at MIT. I'll flash you the 2-minute card when you're at 5 minutes.
Okay, thank you.
Thanks. All right, so hi, I'm Sam Silva. I work with Colette at MIT, and today I'm going to be talking about dry deposition of ozone to vegetation in the model. So kind of a good link with what we've talked about already. We all know that dry deposition is an important loss process at the surface, but just really quickly, the dry depositional flux in nature is dependent on a lot of really complicated surface processes, including turbulence, surface chemistry, and plant physiology. Obviously, we don't really have the computational power to explicitly simulate that in GeoChem, so we parameterize it fairly heavily as a function of the dry deposition velocity, which is calculated using the resistor and series approach. The ultimate goal of what we've done here is to try and assess this parameterization by comparing it to observations and see what we might be able to learn. We focused on ozone dry deposition to vegetation here, primarily because we actually have a decent number of good observations of that process occurring. So speaking of those observations, we sort of went through all the available published literature that we could find and gathered around 78 total published data sets of dry deposition velocities. These have various time resolutions, but they happen to be across all 5 major vegetated land classes in geochem. Those are coniferous forests, deciduous forests, rainforests, grasses and shrubs, and crops. And the distribution of them is shown in that plot up there. So we have pretty decent coverage of North America and Europe, and then some rainforest sites throughout the tropics. I wanted to say that these observations are available for sharing if you want to do your own assessment of dry deposition, but let's talk about mine for now. So this is the bulk comparison. Plotted on the x-axis are observations, on the y-axis is the model. The points represent the means across a given data set, and the error bars are the standard deviations. They're split up by panel according to land class, and they're colored by season. And the big take-home message here is that we actually do a fairly decent job given how heavy our parameterization is. We're generally within a factor of about 1.4, and there's no apparent super strong seasonal bias. In general, we do underestimate dry deposition velocities, and this is true for all land classes except for crops. Now, obviously, we can do a better job than just comparing means by taking advantage of the time component of the data, and that's done here with the hourly comparisons. The model's in black, the model is in red, good lord, and the observations are in black. And a big message here is that these sort of biases are not consistent throughout time. For instance, in the middle panel on the top, we do pretty decent over croplands at night, but we do much worse during the daytime. And before we sort of jump down the model's throat and start screaming, we do terrible over grass, let's completely redo this parameterization, it's important to think about some of the issues that come up when you compare surface sites with the model. And the first is that all of these simulations were done using year 2006 meteorology. So all the observations were not taken during 2006, so we went back and used meteorology to simulate the same time as the observations to sort of get a better match. And that comparison is shown here in green, and obviously that green line tracks super well with the red line. And the take-home message there is that meteorology does not play a dominant role in the disagreement between the observations and the model. In fact, looking across the entire globe, the input meteorology to the model does not actually play a major role in the variability in dry deposition velocities that we see, and this is actually consistent with some observational studies that have been done. The next major potential issue with this comparison is that land classes are heterogeneous within a given grid box in geochem, and this can become an issue when you're comparing an observation over, for instance, deciduous forests, and that grid box might only be 20% deciduous forests. So you come up with some weird sort of representation issues that you want to correct. And so to deal with that, we fixed the land classes in geochem to match the observations perfectly, and that is shown here in the blue line. And it's fairly obvious that over some land classes, for instance, the massive underestimation over grass, that's not necessarily because our parameterization is completely out to lunch, but more just because of the way land classes are represented in geochem and comparison issues. But some of these biases are actually still fairly large, for instance, the daytime bias over crops. And so it sort of begs the question of what ultimately this does, how this impacts our ability to simulate surface ozone concentrations. And so to investigate this, we scaled dry deposition velocities in the model on an hourly per land class basis and looked at what the influence on summertime surface ozone concentrations were. And that plot is shown here. Ultimately, there are three sort of big features to look at. One of them is a little hard to see, but there are two decreases. There's a decrease in the northern boreal forests and a decrease throughout the tropics. And this comes from our underestimation of dry deposition velocities in the model over forested land classes. And then there's this broad increase throughout the mid-latitudes, and that's associated with us overestimating dry deposition velocities to crops. These changes are on the order of 4 parts per billion, and relatively they can get up to 20%. So this is actually a fairly substantial impact to surface ozone. And so the next really sort of obvious question, I think, is how do we improve the model? What do we do to make it better? Unfortunately, it's not that easy because observations generally only have a single value of a dry deposition velocity with time, whereas we have dozens of parameters working together in our model to reproduce that individual dry deposition velocity. So we can't really easily say that, oh, just tweak the stomatal conductance up or turn off this given parameterization. But what we can do is a sensitivity study of our model and look at what sort of knobs we can turn or what we're really sensitive to within our model now. And so we did that. That's plotted here. What I did is I wiggled these various parameters by plus or minus 50% and looked at the fractional change in the deposition velocity. So if it was linear in that given change, the bars would reach the bottom or the top of this plot. They're split up by land class, at least in color. The oranges and reds are forested land classes, and the blues are the grasses and crops. And the different parameters are the stomatal conductance, cuticle conductance, ground surface, and lower canopy resistances, and then leaf area index. And the take-home message here is that we're really sensitive to stomatal resistances and ground surface resistances, and it's super important to get leaf area index right if we actually want to correctly simulate this surface-atmosphere exchange. So ultimately, if we had measurements of dry deposition velocities alongside stomatal and ground surface resistances, that would be really great for our ability to improve this. And so more data, right? But I'd like to say that this work is still currently in prep, and I'd really be happy to talk to anybody about this and see what you might be excited about. So thanks.
Questions for Sam? In your ozone change plot, was it just the change in stomatal conductance for the ozone dry deposition? And if so, are you considering looking at the effect of kind of all species that are taken out?
So yeah, I only looked at the impact of the bias in the dry deposition velocity as a whole, but it was only for ozone. So I didn't couple it to all the other species because that's a little complicated.
The observations at Harvard Forest show large interannual variability in dry deposition. There was a paper by Olivia.
Yep, yeah, it's sort of that other work I was referring to on that slide. Yeah.
And so I was wondering if you have any explanation for this large interannual variability, which you showed, we don't seem to capture at all in the model.
Right, and she sort of shows in her paper that this is largely due to the non-stomatal uptake. And I've done comparisons between. She speculates. Yes, well, I think that's what we do a lot with dry deposition. But I don't have a very strong opinion other than what she's done. No.
I guess I just on that point, the plots that you did show where meteorology year to year doesn't change it, is that like that's like the whole globe of that land cover type put together, right? So it could be that local things have much more variability year to year, or am I misinterpreting that?
So this plot right here generally shows this is only over sites where we had measurements. This is an observation measurement comparison, and it shows very little disagreement. But even when you plot sort of the interannual variability associated with input meteorology, the variability is not very strong, maybe 15%, something like that.
Okay. Our next speaker is Yishuan Wang from the University of Houston. I'll show you the 2 minutes are left guard at 5 minutes.
Good morning. Today I'll be talking about the impact of drought on atmos chemistry, focusing on a region in the U.S. Drought is a natural variability in the climate system. So the major effect of drought is lower precipitation coupled with high temperature. And together, the leading land surface changes and chemistry and deposition changes and more frequent fires. All of these have impact on atmospheric composition. So in this investigation, we first want to quantify how significant those impacts are and how good are the models able to reproduce those. So we focus on U.S. because it's a data-rich region, and it turns out drought is quite frequent extreme in the U.S. So here I'm using this standardized precipitation evaporation index, SPI drought index, to represent the frequency of drought in the continental U.S. So in this study, we focus on growth season because that's when drought has the most significant impact on the land, and also that's when the ozone is highest. So we can see that over about 60% of the U.S. would see a drought frequency larger than 10% over the past 25 years. So that translates to about 20 months. So these black dots indicate those larger than 20%. And also, if you look at the geographical difference, you can see West U.S. and Southern Great Plains, including South U.S. and Southeast U.S. are most drought prone. The reason we select this SPI index is because it's multi-scalar, so I could select 1 month index to represent 1 month drought, and I could also use 6 months or 12 months to change the drought frequency. So in this study, we focus on drought longer than 1 month with most direct implication for air quality. So the data, we just get EPA's data from CASNet for ozone and also improve. So we got the data over the growth season, we have monthly mean, daily mean, average, and monthly. And for the geoscan model simulation, we use MERA 2x2.5 for the past 25 years, and we use year-to-year change in anthropogenic emissions and also year-to-year change in fire emissions. When we talk about the drought pollution relationship, all the air pollution data, we trended and deseasonalized by removing the 7-year moving averages for each month individually. So let's see what observation shows. So here are the slope of a linear correlation between this SPI drought index and ozone shown on left, and the PM 2.5 over the US over the past 25 years. The data are presented at sites that with more than 10% drought frequency. So the correlation, negative correlation means more pollution during drought because SPI is negative under drought conditions. And then the positive correlation means less pollution. So that is this color bar is used throughout my talk. I think the striking feature here is a majority of the sites show significant negative correlations between drought index and air pollution. So that means higher, we tend to see higher ozone and PM 2.5 at the surface with increase in drought severity. And you can see the regions, eastern U.S. is more sensitive of ozone to drought, and then in the PM 2.5 as well. So we use this observation, so this is the same data, but as the previous slide, but mapped down to geoscan grid with a slightly different color bar and compare with geoscan simulation. Top panel are for ozone. We can see that the model generally reproduces pretty well the negative correlation between drought index and ozone over the whole United States. But for PM 2.5, the color didn't show well, but this is a negative correlation throughout the central U.S. So this negative correlation means that in the model, we didn't reproduce the enhancement of PM 2.5 and the drought conditions. So we also did evaluation of some coupled climate chemistry models from this ACCMap archive, which is an older version of the models. So here I'm showing observation compared with two models of interest to this community, NCAR Chem 3.5, which is pretty old version, and also GIS model. So you can see that those coupled climate chemistry models also can reproduce the spatial prevalence of the positive correlation, negative correlation between ozone and drought, but has more variability in their ability to reproduce PM 2.5 response to drought. So for the coupled climate chemistry models, emissions play a significant role in causing these discrepancies in the correlation. Now, what are the effects that are causing the drought effects on ozone and PM? So first, for ozone, is the most important thing is higher temperatures and also lower cloud bursts will lead to higher rates of ozone production. Most models are able to get this, so that's why we see model reproduce this overall very good representation of the negative correlations throughout. Secondly, is connected to the previous talks. The drought would expected to reduce dry deposition of ozone through reduced stomatoconductance, because when the plants are under water stress, they would tend to reduce the stomatoconductance that would reduce ozone dry deposition. So recent publication from Jennifer Murray's group, University of Toronto, they found this vapor pressure deficit on daily scale would tend to tend to drive the ozone liabilities. And for a study in Texas, they found like 20% reduction of dry deposition. But the models are really lacking this response. The third point is response of biogenic emissions to drought is highly uncertain. So I'm using this pretty sparse network from EPA and see this actually increase of isoprene concentrations with drought index in the US. And the model kind of not able to reproduce this except for Southeast US. The drought effect on aerosols are more complicated. So let's look at the observations on individual species. First is organic aerosols are the largest driver of the response. So always all the regions show increase. Sulfur is still second largest increase, especially for the eastern region, and dust is visible for west and Great Plains. So let's look at the organic aerosol to drought relationship. So the model, the take-home message is the model is able to reproduce this correlation, and this correlation is mostly driven by increase in fires in the model. We do not know how SOA responds because we don't, for the EPA emission data, we don't have this SOA observation separated. Big suffice for sulfate. So the observation shows increase of sulfate and the drought, but the model suggests a significant reduction over Southeast US that links to a reduction of aqueous phase reactions. So I think this is maybe this gas phase would increase during drought conditions, and model are not able to reduce this. So here's my conclusion here. So I will leave it here, but we have a paper in discussion, ACPD discussion. In that, we also do a future projection using this observed drought pollution relationship applied to the climate model derived drought index and to estimate what's the impact. The impact is large, but indeed we're still working on this issue and would like to collaborate with people on different aspects. Thank you.
Maybe if there's one quick question for you, Sean? Loretta?
So we've also discovered this, but we only looked at temperature, the effects of changes in temperature on PM2.5. Have you divided up the response of PM2.5 temperature and then to other drought?
No, we haven't do that. We are aware of that work is Lucian published on HCPD. So I think the temperature, the lack of temperature response of PM 2.5 over South U.S. actually, I think is consistent with what we show here. So with this SPEI index, we look at the combined of temperature and precipitation together. So, but we haven't really separated those two because I think for the drought index, it's really its specialty. I mean its uniqueness to have these two combined together. So I think a portion of this may be driven by temperature. Yeah.
Thanks, Yushuan. Okay, our next speaker is going to be Shiliang Wu from Michigan Tech. I'll show you the 2 minutes left when you're at 5 minutes.
Yeah, sure. Go to you.
Hello, good morning, everyone. So this study is, we are collaborating with Dr. Alex Gonser from UC Irvine. And I think this study is a little bit different from our routine studies in at least two perspectives. So one of them is that we're doing actually pretty simple science here, I think. But we are trying to reach out beyond the air quality atomic chemistry community to see that if we can use our research to affect people's decisions, to lead to difference in people's activities, to make a difference, in a good way. So, the second is that I think at this end of, you will stay with me for just several minutes, and I think that at the end of this, my presentation, probably I will give everybody a free gift. So that's, nobody like that? So a free gift for everyone. I just need to check, I have my credit cards. So that, obviously, so at this meeting, I believe everybody knows that some trees could cause air pollution, right? So that, and it can emit, some trees, I would say that, so can emit VOCs, biogenic VOCs, isoprene, monoterpenes, and so that they can lead to the production of ozone and aerosol, okay? And so, there have been lots of studies measuring, so all kinds of different trees, how much ozone they can emit, right? So some are emitting more than the other, so that you can see this study from about 15 years ago, so that, so these are definitely well known, okay, well known, so that even former President Reagan, so that knew this, obviously. So trees, some trees could cause air pollution. But then, of course, and I'm not sure if the current administration knows this. And then another thing we found is that some very important people are not fully aware of this. So especially I'm talking about the people involved in the afforestation or reforestation projects. So that if we look globally, so that currently, so that we have lots, many agencies or organizations so leading, having these different initiatives, so campaigns, planting just lots of trees. Okay? And so that worldwide, so that we have more than 1 billion trees planted each year. If you look at it in the past 10 years, 20 years, so that. And so that one question is that, so what kind of trees are being planted? Right? So we know that all the trees are good for climate, but then there's additional factors to consider. So I have talked to some leaders from these organizations, okay? So most of them from the US, and some are from Europe. So that when I talk to them, so I ask them, simply ask them in thinking about what kind of trees to plant. So what are the factors you think about it? So I got lots of good reasons. So think about erosion control. Think about the potential economic values. See whether you want to plant some trees that can produce nuts, fruits, and also some trees may look better than the others. Okay, these are the responses I got, but none of them have considered air quality. Okay, so that's a surprising, very surprising factor to me. So then we wonder why is this the case? Okay, so of course so one of the response I got is that so we don't know about this. Okay, this is one of them, and then we do not have the expertise to look at how much would be the effects on ozone or on other pollutants. Okay, and so well that seems like that's very good. Execute actually is perfect execute, lacking expertise. So because that we know ozone chemistry is non-linear, we know that not everybody can run air quality models, and so there's a very large spatial variation in the sensitivity of these pollutants to precursor emissions. For example, what I'm showing here is that from geochem, the emissions of aspirin is one of the biogenic emissions, right? And then the ratios between NOx and between NOx and aspirin. Obviously, that's a relative abundance of NOx and VOCs will affect the sensitivity of ozone to these biogenic emissions. Okay, so I was thinking, so what I can do? Okay, what I can do to help them to make it easier for them. So that one of the things so that we learned is that the ODP, and so that the ozone depletion potential, right? And so that the global warming potential. So I think we can develop something we can call air pollution potential index. Okay? So basically, you look through the sensitivity of each pollutant, whether it's ozone or PM, and then look at the sensitivity to the emission factors, how much specific tree species would emit. And then so that you can calculate what would be the specific contribution of that tree species to the air quality. And then so that I think the final product so that we can make some cards, okay, so like pocket cards, brochures, we can hand this out so that help people to understand this and also that we can put application so that out there so that I got the name so that called the app so that air pollution potential index so that and so that if you go data to you just put in the region and season tree species, you will find out about what's that. If you click on Boston, so that you will see that that's you only got 2 seasons, winter and summer. So some of you may think that's a bug. It's not. So if you have lived in Boston long enough, you know we only got 2 seasons, right? So yeah, I think that's it. So that that's a free gift I mentioned. So that hopefully I didn't disappoint you on that. So.
How well do you know the isoprene emissions of these different tree species?
Yeah, so I suggested by Colette, so I need to repeat the question I get. So that the question is that how confident we know about the aspirin emissions from each tree species. I think, yeah, that's a very good question. So we get some data from the literature. So that, as I showed at the beginning, so there are all kinds of different tree species as listed here. There have been some measurement. And also that we are collaborating with Alex Gonser, so that is super nice. So he promised that, oh, if you see any tree species you don't have that, I'll help you measure it. So let me make sure so that I get the question right. So the question I think is that the calculated air pollution potential index compared to the average natural forest. Is that right? Good. So yeah, I get it. So that's how this air pollution index works. So that I didn't explain that in too much details, but basically, so that on the top you see that we're looking at each tree species. Okay, so each tree species, whether it's oak, maple, so that black gum, so that each of them they have their own emission factors. We call it for aspirin, monoterpenes, and then. So this we also have the regional average. So these will account for all these different tree species, okay, based on the fraction of each area, okay, how much you have that. And then you do an average. So if you get the value is 1, meaning that you get the value is close or the same as a natural forest. And if this is above 1, you want to avoid that because you will be planting some trees that's having more air pollution than the natural forest.
Thanks, Julian. Okay, our next speaker is Mingwei Li from MIT. I'm going to show you the 2 minutes left when you're at 5 minutes.
Thank you. Today I will introduce our project about the effects of climate change on Trans-Pacific ozone using a framework that is developed at MIT. So I worked with my advisor Noel Salim and several students and postdoc and researchers at MIT on this project. Well, previous literatures have found that the Trans-Pacific ozone from China has been increasing in recent years. This is largely because of the increasing anthropogenic emission of NOx from China. Also, despite the potential changes in anthropogenic emissions, the question we really want to address in this project is how would Trans-Pacific ozone be influenced by climate change? Here we are using a modeling approach, and we couple the global system model, the MIT IGC8 model, with the general circulation model, the CAM model. So the advantage of our framework is that it's computationally efficient to study the climate uncertainties. The MIT IGSM has both the socio-economic model and an Earth system model with a 2D atmosphere and 3D ocean. So this allows us to look at climate sensitivities from different aspects, like from emissions. So we have both with climate policy scenarios and without climate scenarios. And these are kind of similar to those RCP scenarios. And this model is also flexible to vary some climate sensitivities. Here it's ranging from 2 degree to 6 degree in response to a double of CO2 concentrations. And we also simulate 5 different initial conditions to account for the effects of natural variability. So you can tell that if we drive GeoScan with this whole ensemble, that requires a huge of simulation time. So as a first cut, we only drive GeoScan with one set of climate, that is a no climate policy scenario, and we choose middle climate sensitivity 3 degree 1, and then with one initial condition. So what we do is that we run GSCAM for 20 years around the year 2000 and 2100 as a present day and the future. And the reason we choose 20 years that previous study in our group, we found that we need a minimum of 50 years to identify the climate influence on ozone. And for the anthropogenic emissions, we keep it constant in all the simulations. And because in this project we are interested in the trans-Pacific ozone, we did additional simulations to zero out all the Asian anthropogenic emissions to separate the Asian ozone. And I should mention that for these sensitivity simulations, I only have 3 years from now because we found an unrealistic response of the lightning marks to future climate. So we will definitely do more years of simulation when we fix that problem. So here all the plots shown here are the results from the 3 years of simulation. As I said, this is a no climate policy scenario. So the emissions of those climate forces will increase a lot. And here I plotted the temperature changes in the 21st century, both in summertime and in wintertime. You can see the increase can be as large as 10 Kelvin. And in response, the surface ozone concentrations increases in the continental regions, and this is a well-known phenomenon in the community as the climate penalty. And if you average over the U.S. region, the average climate penalty is about 4 ppb in the summertime and slightly lower in the wintertime in our simulation. And then if you subtract the Asian part, and then you can see the changes in Asian ozone. And because the trans-Pacific ozone has a vertical feature, and so here I plotted the changes in Asian ozone in 3 different levels: the surface, the mid-troposphere, and then the upper troposphere. So we see that there is a general decrease of surface ozone over the Pacific and then over the whole U.S. and it can be judged as 1 ppb. And the reduction is higher in the mid-troposphere and then lower in the upper-troposphere. And we think this is probably driven by a decrease in the ozone production, as here I show the percentage change in PAN concentrations. So you can see that the changes of patterns in PAN, it correlates very well with the changes in ozone. So we think is that the higher temperature that enhance the PAN decomposition that leads a decrease in this Asian ozone. And lastly, if you compare the changes in Asian ozone average over the whole U.S., that is shown in the blue bar, with the changes in surface ozone in the yellow bar, actually this reduction in trans-Pacific ozone, it offsets about 20% of the total change in this surface ozone. And I said we only have 3 years of simulation, so to give you some confidence that this is results still relevant, I showed the changes of surface ozone from our 20 years simulation that is shown in that yellow bar. So we are so the standard deviation is kind of similar. So we are lucky enough to get the interannual variability, given that we only have 3 years of simulation, but the effects is kind of lower. And so the interannual variability in the Asian ozone is relatively small, as shown in that arrow bar of the blue bar. So probably they are driven by different factors of the interannual variability. So we'll definitely do more years of simulation and then more climate ensembles in our simulation as a next step. So I'll leave the summary here and happy to take any questions you may have. Thank you.
Do you think that things would change much if we were using a high top model that would get some of these stratosphere influx of ozone?
You mean model with the stratosphere chemistry?
Yeah, so you would actually result more changes in the stratospheric circulation.
Yes, I never thought this question, but yeah. I mean, in the model we are using, there is like no real stratosphere chemistry, I think. So yeah, I mean, we don't look at how the exchange between the troposphere and stratosphere, and how that, which we didn't like look at at all. But yeah, it's.
It seemed like when you looked at this transpacific transportation ozone, so you had the decrease at the surface, but you had a big increase in the upper troposphere, particularly in the upper tropics. And I'm wondering whether there could be a strong ozone feedback associated with climate change from this.
Yeah, I haven't thought that clearly, so I couldn't like give more.
Big band of
Right, yeah.
the increase of ozone at deck, yeah, right there.
Yes.
I mean, that seems like tremendous negative feedback.
Yeah, that's interesting next step, I think.
Chris, did you have? No? Great. Thank you. All right, our last talk of this first morning session is by Lu Shen from Harvard. I will show you the card that says 2 minutes left when you're at 5 minutes.
Thanks for the introduction. And today I'm going to talk about the influence of climate change on US PM 2.5 concentrations. I'm working with Loretta and Lee on this project. I also want to thank the help I have received from Hongyu and the Jacob Group. So when we predict future PM 2.5, one method is using a chemistry transporter model. But as summarized by these two review studies, the projections of influence of climate change on PM 2.5 are very inconsistent among these studies. Here's one example here. This study displays the concentration of changes in concentration of PM 2.5 by 2050s in July. And you can find this increase in the northeast, but a decrease in southeast. However, a more recent study predicted a totally different pattern in the same month by 2050s. What's the reason for this? If you read these papers in more details, you can find that these studies, they have never evaluated the long-term sensitivity of PM 2.5 to the major meteorological variables. So we did this evaluation in this project. This figure displays the slope of summertime PM 2.5 concentrations to temperature in observations. And we can find this positive sensitivity over the eastern United States. Here are similar results, but using the output from 5 different chemistry transporter models. And you can see these models, they are not able to reproduce this pattern. This is for geoscam. It has this positive sensitivity in the summertime in the eastern US, but the negative sensitivity in the south central regions. Since we run geoscam here, so we can get more detailed output, and we can try to diagnose the reason for this underestimate. So this is for the sloping observations. This is for geoscam. And we calculated these slopes for each component of PM 2.5. And this is for sulfate, for organic aerosols, for ammonium and nitrate. And you can find this in observations. The sensitivity of sulfate to temperature is positive, but in geochem it's negative in south central US, but positive in northeast US. For other species, the discrepancy between geochem and observations is tiny. Taking this together, we can conclude that the underestimate of PM 2.5 temperature sensitivity in geochem is caused by some problems with simulations in sulfate. So in geochem, in atmosphere, there are two important pathways for SO2 oxidation. One is the gas phase oxidation by OH. The other one is the oxidation in aqueous phase by H2O2 and ozone. Using geochem, we found that in the summertime in the eastern US, about over 80% of the oxidation occurs in clouds. So this motivates us to evaluate the sensitivity of cloud fraction in the lower troposphere to the temperature in the summertime. So this is the sensitivity in observations, and we don't find any significant sensitivity. But in GEOS 5, we find this significant negative sensitivity in especially in southeastern United States. So this means when temperature increases, the cloud fraction decreases too fast in GEOS 5. And then this leads to the reduced production of sulfate and reduced PM 2.5 concentrations. Since this CTM doesn't work so well, so we decided to use a statistical method. As a first step, I want to show you it's very important to consider the influence of synoptic patterns on the PM 2.5 variability. This figure displays the correlation of PM concentration in this grid box with temperature in the surrounding regions. I use monthly mean temperature and monthly mean PM. And for this figure, I just use the PM concentrations in this one single grid box, but I use temperature for every grid box. We find this positive correlation over most grid boxes in eastern US. And we did this for humidity, precipitation, the wind. Most interesting pattern is this figure. If we use, this one means if we use the local wind speed to predict PM concentrations, we get no significant correlation between PM and wind. But we find this significant negative correlations in the Western Atlantic and positive correlation in Great Plains regions. So this suggests an anticyclone here. So if we need to predict the PM concentration variability, we need to consider this information into the regression model. We developed a new method to include these synoptic patterns into the regression model using SVD patterns. You may remember this pattern, which is the correlation of temperature and PM I just showed in the last slide. We have 5 different variables, so we have those spatial information in this big matrix. Because we only have a short history of PM 2.5, we need to compress this big matrix to some smaller values. So we have this matrix, we stack them together, resize this matrix, and we apply the SVD to decompose this matrix. After decomposition, the left matrix refers to the spatial weight, and the right matrix refers to the variable weight. And each element on the diagonal of L of this matrix is the magnitude of this oscillation of these synoptic patterns. By including these synoptic patterns into the regression model, we find we can increase the R square between predicted and observed PM concentration from 34% to 43%, which is a significant increase. And then we apply this model to the predicted climate using from 19 IP system models. We found this
increase in the eastern United States, in the summertime, mainly due to the oxidation, faster oxidation and more biogenic emissions. In the wintertime, we found this decrease, mainly in Intermountain West, due to the decomposition of ammonium nitrate. And the average over the year, we found this increase in the eastern United States and a decrease slightly in Intermountain West. And we have this paper just published in ACP 2 months ago, and for more details, you can go to this paper, and this is the end. I'm happy to take any questions.
Are there questions for Luke? Prasad?
Can I ask a question that the decrease in sulfate with increasing temperature of geoscan, that you don't see in the observations, could it simply be because geoscan is not capturing durability in SO2 emissions associated with increased air conditioning use or something as on hotter days?
Yes, this could be a reason for that, but I haven't checked this before, so I don't know if this is really important, but I can show you some more details about the sensitivity of SO2 oxidation rate to the temperature. And this is mainly caused by the aqueous phase. And the sensitivity in gas phase is not that important. These two are more related to the aqueous phase, so we think maybe the cloud fraction should play a more important role in this pattern. I think this is a very good question, and I think we need to investigate in the future work.
Any other questions? Okay, great, excellent. Great, okay, so we have 30-minute poster presentations, 30-second poster presentations, so if people want to come down.
Is it like, yeah.
Do they fit if you put it on full screen?
Yeah, I think so.
Hi, I'm on behalf of my colleague to introduce his recent work on Beijing severe haze. And as we know, the conducive weather conditions are an important ingredient to severe haze episodes. And here we project that the circulation changes induced by the global greenhouse gases can make Beijing severe haze 50% more frequent under the RCP 8.5 scenario. And for more details, welcome to poster C1.
Right, so I guess many of you know that agriculture and fertilizer use in China is extremely inefficient and leaking so much ammonia into the environment. So we want to see whether, like alternative farming method like growing maize together with soybean to reap the benefit of nitrogen fixation of soybean can actually help reduce nitrogen emission. So we use DNDC, sort of like offline coupled with geoscan. We scale down massage ammonia to see the reduction in inorganic PM 2.5 and the reduction in health costs. So please come to see the poster.
So we investigated the relationship between the West Pacific subtropical high and the surface ozone over eastern China on the variation on a daily scale using the UF analysis and normalize the WPSH index. So if you are interested in it, welcome to the poster C3 for more details. Thank you.
Hi everyone, I'll be presenting the impacts of future climate change and land cover land use change on the wildfire emissions of tropospheric ozone precursors and atmospheric mercury. Our major results indicate that significant agricultural expansion in the future could reduce African emissions of wildfires. And in the boreal parts, climate change and land cover change could increase the wildfire emissions of ozone precursors and atmospheric mercury. For further details, please visit my poster and I'll be happy to answer them. Thank you.
Humans have altered somewhere between a third and a half of global terrestrial land surface, and of course that modulates biosphere-atmosphere fluxes and has implications for atmospheric composition. So in this study, we looked at the impact of land use change from 1850 to present day on ozone and secondary aerosol formation, and we used the land module that Jeff Geddes put together when he was visiting my group at MIT, and the results are on poster C5.
Hello, come to my poster if you want to go on your own, choose your own daily maximum 8-hour ozone adventure where you choose a model and parameters, you choose a region of interest, the continental US or a grid cell, and then a window that you're averaging over, and I'll give you error bars for your estimate. So please come on my poster.
Hi, everyone. This is a picture of Arctic haze taken by Eric Court. Observations show really steep declines in sulfate concentrations over the Arctic over the last 30 years. Please come to Tom Breeder's poster to find out what this trend means for the regional climate of the Arctic. Thanks a lot.
So surface measurements show that fine dust levels have been increasing across southwest U.S. regions between 2002 and 2015 in March. And we investigate the reasons for this increase by performing a systematic statistical analysis to quantify the role of meteorology and natural climate variability in driving springtime fine dust variability across the western U.S. in general. So to find out more, please come check out poster C8. Thank you.
Okay, great. So that is the end of our first morning session. Thanks to all the speakers. And there's coffee outside, and we'll reconvene at 10:50.
right. Okay, we're going to get started with the session on air quality and implications. I just want to say two things first. One is that I apologize to every speaker in this session for how I pronounced your name. The second is that I'm not going to do what Colette said she was going to do. I'm going to show you the 2-minute sign at 5 minutes, which means you've got 2 minutes left to keep speaking. So without further ado, our first speaker is Irene Deducey from MIT.
Hi, is this... hi everybody, thanks for the introduction. So my presentation is on using the geoschem and its adjoint to estimate a variety of human health impacts from combustion emissions. So this is just a big picture of what happens. We have anthropogenic combustion emissions that lead to a formation of pollutants such as PM2.5 or ozone that people get exposed to, and that has adverse health impacts. The big picture methodology or method of what we're doing here is we go from anthropogenic combustion emissions to concentrations using the geoschem and its adjoint. We overlay population data to get population exposure, and then we use epidemiologically derived concentration response functions to link this exposure to an increased risk of health impacts, and in particular we usually quantify health impacts in terms of early deaths. So what I'm going to speak about today is I'm going to give an overview of some of my work and the work that we do in our group. And I'm in particular going to speak about how health impacts from the US anthropogenic combustion emissions of different sectors. As in to present that, I'm going to speak a little bit about some work that we did a year and a half ago on the Volkswagen defeat device and the excess NOx emissions from that, as well as I'm just going to give some overview on some supersonic aircraft work. Starting from the sectoral work in the US, we know that anthropogenic combustion emissions in the US is the driver for PM2.5 population exposure, and PM2.5 population exposure is one of the leading also health impacts of anthropogenic emissions. So what we're doing here is we're trying to attribute those impacts back to the different emissions sectors, so do this in a policy relevant manner, so something that we could in theory use later on. We use the geoschem adjoint sensitivities for the North American domain. That's in the 1/2 × 2/3 resolution. And those sensitivities essentially quantify how a change in a perturbation in the emissions contributes to or affects the aggregate US population exposure. And then we use the emissions from the different sectors, assuming that those emissions are a perturbation in the emissions and assuming a linear relationship as shown on the bottom left. And what you see on the right-hand side of the slide is that out of the 170 to 200,000 premature deaths that occurred in 2005 in the US, how these get attributed to the different sectors. And we see that a quarter of these come from the electric power generation sector, around 30%, a little bit less than 30% from road transportation emissions, another 40% from commercial, residential, industrial activities. We also attribute this to the specific species of those sectors, and some of them are more sort of expectable than others. So for the electric power generation sector, 75% of the impact comes from SO2 emissions from that sector. What we found, which was really interesting, is that in the road transportation sector, a significant proportion comes from the ammonia emissions, and in particular, basically any ammonia emissions in high population centers do seem to have some significant impact. For those interested, aviation is fairly small right now, but aviation is the sector with the highest growth rate, estimated to be 5% every year. So even though emissions from other sectors are going down, aviation is expected to increase. And just a quick note, as I said, emissions from other sectors are significantly going down. What that actually implies is that this changes the atmospheric composition and thereby changes the atmospheric response to a unit of emissions, which is what essentially the sensitivity quantifies. So we're doing some ongoing work on looking at how the sensitivities that we use changed between 2005 and 2011. And just a quick overview, we actually find that the sensitivities with respect to NOx emissions increase, which that essentially incentivizes further NOx emissions reductions.
Quickly going on the Volkswagen defeat device work, so as I'm sure many of you know, back in September 2015, the EPA announced that certain Volkswagen car models sold between 2008 and 2015 resulted in significantly higher NOx emissions than those than the regulatory limit and those they said they were going to emit. And basically, we used similar approach to the previous slide. We used the adjunct sensitivities to quantify what the health impacts of those excess NOx emissions was. So we used sales data for those cars. We used a car fleet model to sort of estimate how many kilometers or miles those cars are being driven and what those emissions are. We used a spatial surrogate to attribute those emissions so spatially of where people drive diesel vehicles in the US. And we found that from the emissions that occurred from 2008 to 16, that led to around 60 early deaths and around $450 million of societal costs. And we also quantified what the benefit is of bringing those cars back into compliance and what impacts that would have. So that would avoid around 130 premature deaths and around 800 million of societal costs avoided. And there's a poster on that by Guillaume, on some work that we're doing in the European domain. So feel free to stop by if that's of interest to you. And finally, I've spoken about a lot of PM2.5 and ozone exposure impacts, health impacts. There's another sort of source of potential health impacts, and that is through UV, exposure to UV radiation, through ozone depletion. And that's of interest to us because supersonic aircraft are expected to, or if they would fly in the stratosphere, and NOx and water vapor emissions from those would deplete the ozone. So there is significant uncertainty in supersonic aircraft emissions, and we're therefore looking for an approach to examine the entire design space of possible impacts, which is why we're doing the development of the UCX. And there's some ongoing work that we're doing right now, which I'm going to leave out because I think I've run out of time.
deaths and economic impacts. Have you considered any uncertainties in the different toxicities of different types of aerosols? So when you attribute the impacts to different emission sectors, they're emitting different types of aerosols, which may have different health impacts. Is that considered?
Yeah, so no, this assumes equal toxicity between the different PM2.5 constituents. But that's something that would very much be interesting, especially with black carbon.
So you find that ammonia is an important agent for the transportation sector. But what about the agricultural sector? Mm-hmm. Is this something that you've looked at?
This is not something that we've looked at. It's something very interesting. This is all combustion emissions, anthropogenic combustion emissions, yeah. But that's certainly something of interest.
All right, let's thank Irene again.
Thank you.
So our next speaker is Jintai Lin from Peking University, and I just remind all the speakers to repeat the questions so the people on the webcast can hear. Jintai.
Okay. It's now coming up. Okay. First, I want to say. Okay. So this I'm going to present several works of our big group, including my group as Qiang group and several other groups in North America and Europe. So I want to say our studies so far has officially has little funding. Okay, almost zero funding. We just do it for fun. So hopefully you also think this is fun stuff. As we always do, we apply funding for things we are interested in, but we do things we really want to do. Okay. So as I say, this is my collaborators. I put this funding here, but those are not actually officially supporting my activity here. So anyway, so today I'm going to talk about this globalizing air pollution. And so I'm trying to give you some examples of what this globalizing air pollution means for the air quality, for the climate, and for ecosystems maybe. So globalizing air pollution means first that pollutions once are emitted from somewhere, say a polluter, producer. Normally it's related to economic activities like factories, power plants. And so once pollutants are emitted into the atmosphere, it can be transported somewhere else, say from China to United States, they will have seen talks about. But also in this globalized economy, when we are sitting here, I think probably every one of us has been buying stuff, this foreign stuff. They are not actually produced in another country, another place, not locally produced. Okay, so and this trade and globalizing economy means that production as well as the association emissions are actually moved virtually, but it's not physical, but moved from the region which are supposed to consume and produce the product to a region that really produce the product to supply the consumption. So, and these two processes are actually not separated. It's actually very highly coupled, as I will show you some examples. So the first example, which is also the first study that we did on this topic, is to look at how China's exports is affecting China's air quality as well as the air quality in the United States. And this is only an example for sulfate air quality. As you can see here that we find that about 20 to 30%, up to 1/3 of China's SO2 emissions, as well as its sulfate concentrations, actually come from industries that are producing goods for foreign consumption, including the United States. And of course, some of the pollutants can be transported across the Pacific to the western United States, and even to some, Arctic areas. So, and we all know this part. So, this is an example of how these two processes are combined to affect the global air quality, not just local, not just regional air quality, but a global air quality. So just as the factories now are moving from the United States and other developed countries to developing countries like China, within China, we found that similar things are happening. So basically, the richer regions along the East Coast actually moving of industries and including some power plants to the inner regions of China. So, and there's a lot of pollution transfer just due to the industrial relocation within China. And this is now a big issue because China is really want to developing economies in its inner regions. And what's the implications for air quality in the inner regions as well as transport when you consider the atmospheric transfer? And okay. So if you look things to a bigger scale, if you look at the global trade as well as global transport of pollutants, and you can see that in general, developed countries, shown in red here, has more emissions that related to their consumption than their emissions related to their activity, domestic activities, like domestic production. And on the other hand, developing countries used to have, normally has lower emissions related to their consumption as compared to their production. And not just the total number of emissions that matters, but actually the location of the emissions that really matters. For example, this is an example of the black carbon emissions produced in Europe. But this is the emissions That's due to consumption by Europe. As you can see, the emissions are all over the places, all over the world. And this will definitely affect the air quality everywhere. So in terms of what does this mean for climate forcing? We just do a simple comparison of the consumption-based radiative forcing minus production-based radiative forcing. And you can see that for, say, in North America and Western Europe, for, say, black carbon, you can see most values are in red, which is positive, which means that their consumption-based radiative forcing are much larger than their production-based forcing, except for their domestic territory. So almost the other story is true for developing countries, say East Asia. So okay, this could be my last slide. So if you look at, if you do the total radiative forcing calculation, you can see that again, for for developed countries, their consumption-based radiative forcing are much larger than their production-based radiative forcing. And the other story is true for the developing country. This means there's a lot of radiative forcing transfer between different countries just due to trade as well as atmospheric transport effect. Okay. I'll skip this on health because Zhang will talk about it just after me. So I'll stop here by just showing you that this globalizing air pollution is really important, and we shouldn't forget there's many two mechanisms rather than just atmospheric transport. Okay.
Okay, so now you bring up here the issue of a movement of pollution sources within China, to the west.
Yeah.
And you say that there's a big concern in China. Why is this?
Because, see, the East China, Beijing especially, they want to cut emissions and for the air quality concerns, actually. So, so they have also, of course, have a expected reduction on the PM concentration. But if this, and what they did, I mean, okay, some of their actions would be to move factories to other places.
That's a reasonable thing to do.
Yeah, true. But if this effort continue, then they'll have a big problem about emissions. They are relocated to their waste, being transported somehow to transported back, and in the very short term, they will see this kind of effect, and by then, how to deal with this transported pollution? Yeah, I think that's just mimicking what's happening between the developed countries and the developing countries right now.
All right, let's thank Jun Tai again. And our next speaker will be Cheng Zhang from Tsinghua University.
I will follow Jun Tai's talk, talking about the transboundary health impacts of global air pollution due to international trade. So we know we are suffering PM 2.5 air pollution globally, and especially in developing countries. So this figure is from satellite-based retrievals PM 2.5 exposure from Randall's group. And you can see several hotspots in China and India and other countries. We know that air pollution can travel long distance and impact in air quality and relative health in other countries. This is results from the first phase of HTAP study showing emissions from produced in different regions impact global human health. As we can see, actually most of the pollutions are local, but some proportional of the pollution can travel long distance and impact global air quality, especially like if we look at the emissions from East Asia, can see impact, worldwide impact. In the meanwhile, the pollution produced are driven by final consumptions. So that means in our global economy, the locations of emissions can be relocated due to transport of or imports or exports of goods through supply chains. So the location of consumption and the locations of emissions could be separated due to, from international trade. So following several regional studies, so here we combine the 4 global models to investigate the premature mortality due to fine particles embodied in global trade. And we first quantify the emissions produced for each country in 2007 using a bottom-up emission inventory with very detailed industrial sector classification. Then we use a multi-regional input-output model to link the consumption activities and the production activities and trace the emissions from location of production to the final consumption place. Then we use geoscam to quantify the impact of international trade by a series of runs. We have a base run with all emissions and then remove emissions of each region's production or each region's consumption, as Jintai shows in his slide, the relocation of emissions. And then we link our calculated proportional contribution of pollution to global PM exposure from global burden of disease study to calculate the health impact from each region's production and consumptions. So this is a definition of 13 global world regions. So we begin with IPCC 10 regions and then identify several large countries like United States, China, and India, with what we thought they have large impact on global air qualities. Here are some results. This figure shows a worldwide premature mortality in 2007 due to each region's production in left panel and consumption in right panel. So we can see the health impact embodied in international trade has much worldwide or global impact than physical transboundary health impact because we can import goods from everywhere. But from the physical transport, the larger impact always in neighboring and downwind regions. So here's showing a detailed global link between among different regions due to the impact of production. So as we can see, the large impact occurred in neighborhood and downwind regions. Here's an example, about 10% of deaths in Western Europe were due to emissions in Eastern Europe. But those kind of impact are much smaller between China and the US due to much longer distance. However, from a consumption perspective, if we look at the proportional of deaths in a given region linked to consumption in different regions, we see much wider and higher impact. For example, still large impact between Western and Eastern Europe because they are close linkage, economic linkage. But between China and the United States, can see more than 50,000 of premature deaths were linked to your consumption in United States. So here's the net effects. So basically, if you look at the bottom, go directly to the health impact, usually consumption embodied impact in developed countries are higher than developing countries. So this is the final slide showing the production-based and consumption-based mortality from a series of bars. I would like to highlight that also from a production perspective, can see China and India has large impact, but most local. Most impact was staying local. But if we look at the impact to outside in consumptions, the developed regions like Western Europe and United States are highest among the global regions. So our findings quantified the extent of the air pollution is a global problem in our global economy. So I will stop here and happy to take questions. Thank you.
So how do these health impacts compare against the economic benefits of trade? Do you have any way of quantifying those? Can you repeat the question for the webcast?
Not yet. So we know that, so this complicated issue that, so the climate community already talked a lot about the shared responsibilities between consumer and the producers. So this study so quantify the extent, but we didn't go step further to the economic analysis.
Do you have the ability to look at how changes in trade agreement would impact your results?
We are now doing a time series of studies, so looking from beginning from 2001, where we have the global trade data earliest and extended to 2011. So this is ongoing work we are looking at.
I have a quick question. I'm curious whether you've thought about looking at the consumption costs on a per capita basis and whether that would change how much different countries are responsible?
Yeah, we have done that. We have a figure in our paper in supplemental information. So yes, we have done that.
All right, great. Let's thank Chung again. And our next speaker will be Luke Schifferl from MIT.
Hello, I'm Luke Schifferl. I work with Colette Heald at MIT. I'm a grad student there. I'm going to be talking about the impacts of air quality on global crop production. So our motivating question really is, how does air quality affect our ability to feed a growing human population? And this figure shows how global crop production and population are often co-located, and these areas are also suffer from air quality issues, both from particulate matter and ozone. And so the goal of our project is to quantify these air quality effects on crop production and both particulate matter and ozone. And first I'll introduce ozone. Ozone has been pretty widely studied and its effects on crop production, and it always has a negative effect by damaging the leaves and reducing stomatal conductance. And the impacts on crop yield vary by crop type. For example, wheat is more susceptible than maize. The relationship between ozone concentration and crop yield has been quantified through different empirical metrics by basically summing up the ozone exposure and relating this to a specific relative yield by individual crops. And this has been done in several papers before. So if we use ozone concentrations from GS Chem and plot this globally for the different crops, you can see here using 2010 emissions that we see about a 7% reduction in wheat, which is the largest and most sensitive compared to other crops, with slightly less decrease for maize and rice. Particulate matter, however, has a different impact on crop production, and it has been much less studied compared to ozone. So the total shortwave radiation that reaches a crop is made up of two parts: the direct radiation and the diffuse radiation. And when you increase particulate matter, the total shortwave radiation that reaches the plant decreases, but the diffuse fraction of this radiation increases. And this more readily distributes the radiation from the sunlit leaves onto shaded leaves, and that increases the efficiency that the crop can use the sunlight. And several studies have related this diffuse fraction to a quantity called radiation use efficiency, but this relationship is uncertain, and I've looked at several of these different relationships. But we can relate the shortwave radiation to the relative use efficiency and get an approximation for how much carbon was fixed. And so if shortwave radiation decreases and the radiative use efficiency increases, we have, depending on the balance of these two quantities, there might be an increase or decrease of crop yield. And so we simulated PM using GS Chem, and with the RTMG radiative transfer code, simulated the diffuse and direct radiation. So here again is the ozone effect, and then if we add the PM effect, you can see that there's a increase in the crop production, a reduction in the total effect from air quality, and in some locations there's actually a net positive effect where the PM can offset the negative effects from ozone damage. But this is largely varies between crops and regions, and depending on the different sensitivity to diffuse fraction that you assume. So as I said, that this relationship between diffuse fraction and the radiative use efficiency is highly uncertain, and so we can basically quantify these over the different relationships. And so using the different lines on the left to translate to the x-axis here, you can see that when at 0, when you only include the negative effects from the shortwave radiation decreasing, you have about a 5% decrease up to a 10% global increase, assuming 100%. And this varies by crop as well. And region here, we're showing that this effect is less in the US and Canada region and higher in China and Southeast Asia. So we can do the same simulation using future emissions, and if we take the difference between 2050 and 2010 for ozone, you can see that the improvements to air quality assumed in RCP 4.5, where ozone decreases, causes an increase in crop production everywhere except for India. But if we add in the PM effects, you can see that the improvement from air quality improvements decreases, and in some locations, the net impact of improving air quality actually causes a decrease in the crop production because the PM effect is larger than the ozone effect. We've also looked at, we've also included these PM radiation effects in a crop model. This crop model accounts for resource restrictions such as water and nitrogen, provides physiological constraints on growth, and can include shortwave radiation effects on hydrology. So if we compare the relationship between the sensitivity to diffuse fraction and change of PM effects, change of production due to PM. For the offline analysis I've shown already in black compared to this crop model in orange with no water stress and no nitrogen stress, you can see that that for wheat and rice, the two models compare quite well, where there's a difference for maize that we're looking into. But if you add in stresses which aren't accounted for in the offline, more simple analysis, you can see that the effect of PM decreases, and that's simply because these water and nitrogen stresses decrease the ability of the plant to fully take advantage of the increased efficiency from the PM. Just reiterating my conclusions, crop production enhancement due to PM can offset the negative effects caused by ozone damage in certain areas. Future improvements in air quality may have negative effects on crop production by reducing the diffuse light effect, and failure to account for the air quality influence in the crop models may result in substantial model bias. In the future, we'd like to add ozone effects and include some kind of nitrogen cycling from the deposition of nitrogen in the crop model to see what effects this might have on crop production. Thank you.
I'm guessing that the degree to which diffuse fraction affects the crop yield is going to be a function of the physical characteristics of the crop canopy and how closed it is and how much better the diffuse radiation can propagate through. So is that part of what's driving the differences between the crops, or is that not something you're considering?
Yeah, so the question is, how does the basically different structure of the crops affect the diffuse fraction effect? And so we're using the, that all is based on the radiative use efficiency value that comes, has been determined in the crop modeling community. And so that varies by crops, and we're using that same value and then modifying that value based on the diffuse fraction. And so that would be one of the reasons why. The other reason would be that we've sampled the comparison to specific crop calendars, and so the difference of the growing season different time periods of the growing season for the different crops may be differentially influenced by the amount of PM in that time period at that location.
So do you account for the reduction of ozone at the canopy level relative to your surface model height? Use concentration-based metrics?
So no, we're just using the surface ozone value as used by other studies.
A lot of other studies calculate like what the crop or what the ozone would be at 3 meters or 2 meters,
Yeah.
not 50 meters.
Yeah. So we haven't done that yet or looked at that.
Yeah, I'm wondering whether you have done any validation of the PM crop-yield relationship in your work?
No, we haven't looked at any of the actual PM measurements. We've looked at a couple sites comparing the radiation from the RTMG with ground sites, and we can see that there's an improvement, but the variability isn't reproduced quite so well compared for like day to day.
Other things that the crops respond to, so I was thinking about acids or other atmospheric components.
The question was, were there other things that the crops might respond to, like acids? And we haven't looked at any of the other impacts. I'm sure things like deposition of PM onto the leaves and things like that, or oxidation of the surface might be important, but we haven't looked at that.
All right, let's thank Liz again. Our next speaker is also from MIT, and this will be a talk by Tel Feng.
Test. Okay. My name is Tao Fan. I'm from MIT. I work with Professor Noel Celine. Today I'm going to introduce my work on the influence of air pollutant emission controls on the U.S. climate penalty. Climate penalty is the increase in pollutant concentration resulting from regional warming in the absence of precursor emission changes. These pollutants, such as ozone and PM2.5, may impose significant health risks over human beings. The climate change can affect the concentration of pollutants by modification of several meteorological variables such as temperature, wind speed, and precipitation. For example, with a decrease in wind speed induced by climate change, there will be a increase in the frequency of stagnant situation, which will tend to increase the concentration of pollutants. Now I'll draw your attention to the comparison between this polluted world and the clean world. If we if we have the same stagnant situation over these two worlds, in the polluted world, the concentration of pollutants tends to increase due to this stagnant situation because the precursors emitted from the factories and power plants tend to trapped in the boundary layer and will undergo chemical reactions to form ozone and PM2.5. So we will expect a significant climate penalty in this case. In contrast, with the same stagnant situation in the clean world, there's not many precursor emissions. Even with the stagnant situation, we will not expect a huge increase in pollutant concentrations. Therefore, in this condition, the climate penalty should be smaller than that in the polluted world. So this comparison, I want to show you that the climate penalty is not only affected by the climate change itself, it can also be affected by the emission levels. Therefore, we conclude here that the climate penalty is a function of both emissions and climate change. Previous research have been focusing on how climate change can affect climate penalty, and now the research objective of this study is to focus on the influence of emissions on climate penalty. To do that, we utilized the IGSM-CHEM framework introduced by previous presenter Mingwei Li. It is produced by MIT. The IGSM is an integrated global system model, incorporates both the socio-economic sector and Earth system sector. The socio-economic sector will produce forecast for the greenhouse gas emissions in the future, and it will incorporate to the Earth system model to produce the climate projections. It only has 2D atmosphere in this model, so they coupled this to the CHEM, to general circulation model CHEM to have 3D atmosphere. And finally, we link this framework to GeoChem. We only draw a few climate projections from the ensemble projections. We only use the no climate policy scenario, which will reach 10 watts per meter square total radial forcing in 2100. And we only use 3 degrees C climate sensitivity. We only used one initial condition from the 5 initial conditions in the simulations. The time frame in our simulation ranged from 1991 to 2010 and 2091 to 2110. And these are centered on 2000 and 2100 respectively. To look at the influence of emissions on climate penalty, we generated 4 emission scenarios. We used the 2006 emissions as the reference case and changed the non-greenhouse gas emissions in the US only by 50% to generate the REF minus 50% case. We applied the same practice to the last 2 emission scenarios. And they increased the non-GHG emissions of the US by 50% and by 100% to form these 2 cases. The climate penalty show the first 4 plots shown on the top panel suggested the climate penalty of PM2.5 in the United States. We find that when going from left to right, with the emission increases, the PM2.5 climate penalty in the northeastern US, which is where we are now, will increase. And the 5 plots on the bottom panel shows the climate penalty for different species in the reference case, which is the 2006 emissions. We find that when we compare between the sulfate climate penalty and with the climate penalty of PM2.5, we find that the increase in northeastern US of climate penalty of PM2.5 is really induced by this increase of sulfate formation. We also find a decrease in nitrate concentration due to climate change because of the thermal instability of this species. The change of ammonia tend to be spatially inhomogeneous, with an increase in the eastern part and a decrease in the western part, which reflects the increase in ammonium sulfate and the decrease in ammonium nitrate in the west. The change of organic carbon and black carbon tend to be spatially homogeneous with increase in both western part and eastern part of the United States. We also find increasing ozone climate penalty with emission changes. As we go from low emissions to high emissions, the color will become darker, which means that the ozone climate penalty will also increase in both eastern part and western part of the United States. I'll wrap up. We also draw relevant policy implication from this result. The first plot on the top shows the concentrations in both current climate scenario and future climate scenario, and the difference between them is the climate penalty, which is shown on in the green color. If you think this plot is too overwhelmed, I will show you the story through this back of envelope calculation here. If the government carry out the policy to reduce current emissions by 50%, and we will tend to get a direct benefit of decreasing ozone concentration by 1.46 ppb as the difference between the concentration in the reference case and the reference minus 50% case. On top of that, we will also get a decrease in ozone climate penalty in the magnitude of 0.28 ppb, which account for 20% of the direct benefit. We treat it as the indirect benefit of this policy. The takeaway of this study is that we find an increase in PM 2.5 climate penalty in the northeast US with emission increases. We also find a similar pattern applied to ozone. We draw relevant policy implication, and from this we quantified additional benefit from the decrease of emissions as the avoided climate penalty, which account for 20% of the direct benefit of the decrease in ozone concentrations. With that, I will conclude here and happy to take questions. Thank you. Yes. The question I got is that have I think about the feedback from the pollution, the air quality to the climate system? And the answer is no, we didn't include that here. We only the IGSM-CHEM framework, which we draw climate projection from, is only one way coupled to GeoChem, which means that we don't have a feedback from the GeoChem to the IGSM-CHEM. And we really missed some information from this feedback system. And there has been some studies showing that the actually air quality can also modify the climate system by impacting on the wind speed stuff and things like that. But we didn't capture that. Maybe it's left for the future work. Thank you. Thanks.
And in case anyone was worried that we hadn't had enough MIT talks this session, our final talk of the session will also be a speaker from MIT, and we're going to hear now from Katie Mulvaney. Katie Mulvaney.
Great. Thanks for the introduction. Today I'm going to be talking about how my collaborators and I are using GeoChem to examine mercury co-benefits of climate policy in China. So as many of us here know, the Paris Agreement on Climate Change and the Minamata Convention on Mercury are both in the early stages of implementation. China is going to play a key role in both of these treaties because they are the world's highest emitter of both CO2 and mercury. So our group seeks to examine policies that could tackle both of these challenges at once. So our research question is, how do mercury emissions and deposition co-benefits of climate policy in China compare to emissions reductions that could be achieved by end-of-pipe controls that are designed to meet the requirements of the Minamata Convention? And we're looking at our results at both the national level and also the regional and provincial level within China. I'll start off with a quick overview of our chemical transport modeling methodology. So we're looking at 5 different policy scenarios where we project mercury emissions to 2030. We have a business as usual scenario. We have a Minamata Convention scenario where all emissions stay the same as the business as usual case, but we apply some air pollution control device technology factors to coal-fired power plants and coal-fired industrial boilers. And then we have 3 different climate policies that are represented by reductions in carbon intensity for China. And we have 3 different stringencies, 3%, 4%, and 5% carbon intensity reduction. And we implement those as essentially a carbon tax in an economic model that I'll describe on the next slide. I'm taking advantage of the HEMCO emissions component within GIAS-Chem, and I'm using emissions from the EDGAR database for global atmospheric research, or EDGAR. And just a few quick notes on GIAS-Chem. I'm using version 11.01 with present-day meteorology and a 4x5 degree grid. We're hoping in future work to look at some higher resolution results to really get at those provincial and regional interactions within China. And then all of the chemistry settings are standard for the mercury simulation in version 11. To go into a bit more detail on our methodology for projecting emissions to 2030, as I said, I'm using the EDGAR database for mercury, and EDGAR includes 8 different economic sectors that are listed here on the top of the slide. We're using the year 2007 emissions as our base year, and the EDGAR database has a resolution of 0.1 degrees by 0.1 degrees. And it also has global coverage, it's not just emissions over China. In order to scale those 2007 emissions up to 2030, we use the China Regional Energy Model, which was developed by researchers at MIT, abbreviated CREM. And CREM is a computable general equilibrium model that includes information on how provincial economies interact within China, and also how China's economy interacts with the rest of the world. And that gives us some economic output data that we use to create scaling factor masks that we apply to the 2007 base emissions in HEMCO. And as a quick note, we do apply some additional factors to account for end-of-pipe controls that are not incorporated in CREM to both power plants and industrial boilers. And happy to talk about that later if anyone's interested. Moving on to our emissions projection results. So here on the slide, we're looking at national level emissions reductions across all of our policy scenarios. And we see that for some of the climate policies, there is potential for substantial mercury emissions co-benefits, especially for the 4% and the 5% climate policy cases. But we don't see much of a change in that least stringent climate policy at 3% carbon intensity reduction. Most of these reductions are happening in the power and industry combustion sector. And also, an interesting note is that the 5% carbon intensity reduction climate policy scenario sees reductions that are very similar to that Minamata Convention policy case where we implement end-of-pipe controls only. To give you an idea of the spatial distribution of our emissions results, here on this slide I'm showing absolute emissions on the left-hand side for the business as usual case in kilograms per meter squared per year. And then on the right-hand side I'm showing reductions in emissions for all the other policy cases compared to business as usual, and that's in units of delta kilograms per meter squared per year. And as far as absolute emissions go, we see that the highest levels of emissions in 2030 are occurring in central, southern, and coastal provinces. And we also are seeing that the emissions reductions occur the highest emissions reductions occur in those same areas for the other policy cases. Moving on to our deposition results. So here I'm showing total mercury deposition, which includes both wet and dry deposition. And once again, on the left-hand side, I'm showing absolute total deposition for the business as usual case. And on the right-hand side, I'm showing percent difference in total deposition compared to BAU for all those other policy cases. And looking at total absolute deposition, we see the highest levels of deposition in those same areas where we see high emissions in 2030. Moving over to the changes in emissions in each of those policy scenarios, I'll start with that 3% carbon intensity reduction scenario. So we're not seeing very high changes in deposition for this scenario, and in fact, we see a slight increase in deposition in some of those southern provinces. For the other two climate policy cases and for the Minamata Convention case, we're generally seeing total deposition reducing over the same areas where we have high reductions in emissions. But an interesting thing to point out is that our highest levels of emissions in the 5% and Minamata Convention case of about 25% reduction are occurring slightly north of where the absolute total deposition is occurring, and also perhaps slightly north of where the highest levels of emissions are. And with that, I'll wrap up, and I'm happy to take any questions.
We have time for questions for Katie. Okay, Dan.
I was surprised that you have a large increase in the source from cement production from present to 2030. I'm not used to seeing cement production as a big source of mercury. And I wonder if something can be done about it, and why is it that it would increase like this?
So that's a factor. Oh, I'm sorry. To repeat the question, why do emissions from the cement sector change so much from 2007 to 2030? That's a factor of how we're scaling up emissions. So what we're seeing in that economic model is that sector production levels in the cement sector in China are growing a lot to 2030. So that's the reason why we see that. And in this study in particular, we're not applying any additional like end-of-pipe controls for the cement sector like we do apply for power plants and industrial boilers. So I guess that sort of explains the increase.
I have a question about your Minamata application. Do you apply those reductions globally and therefore get any benefit of impact from transported mercury on your deposition maps, or is that purely for China?
So the question is whether we apply end-of-pipe controls in the Minamata case across the world. And the answer is we only apply those end-of-pipe controls in China. And for all of the policy cases, actually, we use 2007 emissions in the rest of the world to really isolate the changes that are occurring in China.
So would you expect extra benefit from Minamata being implemented everywhere?
Yes, probably, yeah.
All right, let's thank Katie and all of our speakers.
Yeah. Oh, yeah.
And let's invite all of our poster presenters down to introduce posters.
Why don't we line up a little bit further this way than everybody else has, because then there's more space. I don't think you do need to stand there, right? Oh, you just pass it? Yeah, we'll just pass it. You guys will take the signs, right? Good to meet you. Yeah, so I'm following this guy.
Okay, so now you're 12.
Okay.
Self-sorting.
Excellent.
Is it on? Yeah.
Yeah.
Okay. Ready?
Yes.
Okay.
All right, let's go for it.
Hello, I'm Forrest Lacey. I'm a postdoc at NCAR, and I want to talk to you guys about some of my preliminary work on province-level import-export of climate and health impacts. And we've used future population and future emission scenarios to evaluate how climate and health is transported between provinces in China. So come see me at my poster at C9 if this interests you.
Okay, hi everyone again. So severe haze from smoke blanketed equatorial Asia in 2015, September, October, the El Nino year. And Shannon Koblitz did a great paper on this, and she answered two questions in that paper. How many thousands of people died as a result of this smoke, died prematurely? And second, how was she able to turn around, to start and submit a paper within 4 months? To find out how, please come.
Hi everyone, my name is Daniel Rothenberg. I'm a postdoc at MIT. And I'm interested in this question of where and when will we be able to detect climate penalties due to a changing climate, and how might that influence how we evaluate health and environmental policy. So come chat with me about that. Also, if you have big data problems, I have high performance, easy to use solutions, and I'd like to show them off.
Hi, I'm Guillaume Chaussière. I'm a grad student at MIT, and I'm working in the same group as Irene. And she mentioned the Volkswagen scandal, but it soon became clear after the scandal that many other manufacturers manufacturing diesel cars in Europe are involved in excess emissions released on the road. And we used the geoscam model to try to quantify the public health impact of these excess emissions on the European roads. So come chat with me. I'm at poster C12.
Hello everyone,
I'm Dan Tong from Tsinghua University, and my work is focused on air quality and health benefit in the global thermal power plants. The left panel will show that in our previous work that we developed the global unit power plant, unit-based thermal power plants, and in this database we have the emission information and location for each unit. So based on this emission inventory, we use the GeoScam model to quantify the emissions, air quality, and health benefit. Thank you.
Hi everyone, I'm Amanda from MIT, and in this work we're asking whether we can detect signals of mercury policy change through environmental loadings in wet deposition given noise from climate variability, and if so, where and how long will it take us? And so to do this, we're driving GeoScam with an ensemble of meteorological fields from the MIT IGSM CAM, and so if you're interested in signal-to-noise issues or climate chemistry interactions, please stop by poster C14.
Hi everyone, my name is Hannah Horowitz. So as you may know, mercury is a global toxic pollutant and humans are exposed by eating fish. I'm going to be talking about the atmospheric chemistry of mercury, and if you want to find out how that's involved in this step from emissions to health impacts, come talk to me at my poster and learn about atmospheric chemistry of mercury. Thank you.
Hi everyone, so this case study is about mercury and Native Americans in Maine. So what might be of interest to the GeoScam mercury community is that I incorporated new emission inventories for 2035 based on this paper published a few months ago. So on my poster, I present global maps of mercury deposition according to 3 different policy scenarios. So if you're interested in the data or if you want to know more about this project in Maine, comment my poster C16.
Hi. People are worried about consumption of fish mercury in terms of human health, but what about the fish themselves? So you can come see my poster, which is about a modeling framework that we're developing involving GeoScam that traces mercury into the health and sustainability of the fisheries themselves. So you can come see it, C17.
Hi everyone, my name is Rebecca Stern. Our group is working on a biogeochemical mercury simulation in GeoScam, and my work is focused specifically on the terrestrial side, updating a GTMM that was originally published in 2010. And this builds upon previous work by Bess Corbett and Nicole Smith-Downey and considers interactions between carbon, sulfur, and mercury in the terrestrial environment, as well as the atmospheric coupling of GeoScam to surface interactions. So I'm at poster C18.
Hi everybody, my name isn't Peter Evert and we're not doing mercury. What we are doing is polyaromatic hydrocarbons, which have become of interest in Europe because of people mainly in rich areas burning wood because it smells nice and is nice at the winter. So we have a surprising air quality problem in rich areas rather than in poor areas. And so we're building a nested grid version of the polyaromatic hydrocarbon. So go and talk to Peter, who isn't here because he's dislocated his knee. So he's currently experiencing the joys of the US healthcare system, and I think the university is probably terrified about what the costs are going to be of that. So if I disappear with a credit card, it's because I'm having to go bail him out. Thank you very much.
All right, let's thank all of our poster and